Welcome, everyone, to Architects and Engineers for 911Truth. My name is Andy Steele. I'm the Operations Coordinator for AE911Truth, and today we are continuing our webinar series with a special guest presenter. I'm honored to introduce him to you. His name is Jonathan Cole. The title of Jonathan's presentation today is going to be The Twin Towers, the Force Behind the Motion. He'll be telling us more about himself in just a minute. Before I turn it over to Jonathan, I just want to remind everyone that if you want to boost the resolution in your picture to better see the slides that he's going to be showing, then all you got to do is simply click on the gearbox beneath the video and select 720 HD resolution. That'll improve it. Also, we're going to be taking questions today, just like we always do, related to the scientific evidence that Jonathan is going to be presenting. So I want to encourage everyone to submit them. We are going to be sticking to questions about the material today. If there's any questions you have about other aspects of the evidence that we go over at AE911Truth, we want to invite you to come back to future webinars with Richard Gage and others that in which we'll be addressing those. So without any further ado, I'm going to hand it over to Jonathan Cole. Jonathan, welcome to the webinar series.
Thank you very much, Andy. It's a pleasure to be here. It's kind of nice to be able to come on your show and follow in Richard Gage's footsteps, so I very much appreciate that. Tell you a little bit about myself. I guess I was like most people in that I believed the official story for many, many years, up till about 2008. I had no reason to doubt it. And then with the miracle of the internet, somebody sent me a video and a couple of scientific issues with the towers fall. And then since then, I've been trying to study this thing and understand what did or didn't happen. And unfortunately, the more I looked into it, the more I realized that what we were told was quite wrong compared to what really happened. And so I decided to put together some experiments. That was sort of my little niche. I'm just a civil engineer. I just do ordinary engineering, but I could do some basic experiments to either prove what could have happened or couldn't have happened on 9/11. And that's sort of what I've done up to now, starting back in 2010. And this is my presentation tonight is the latest experimental things that I did in the last year, again, to try to prove or disprove what happened that day. And again, as you mentioned, the title here is The Force Behind the Motion. And I'm going to be studying the motions. I know Richard had studied the extreme temperatures and the sounds of explosions, but tonight we're just going to focus on the motions that we observed with the towers. And I guess with that, I'll jump right into it. I've got a little PowerPoint presentation I put together. I also have a video on this under my YouTube channel called Physics and Reason. That's much shorter, but the beauty of this is it allows me to kind of get into more depth as far as some of the physics behind it. And it's all pretty much basic physics. So with that, I'll jump into this. So as a little bit of a background for people who are not familiar with the events of 9/11, especially on the scientific side, 9/11 was studied by the National Institute of Standards and Technology. They did investigations, but they never explained a couple of the fundamental motions that we observed with the towers fall. And more importantly, no real models were ever built to demonstrate those motions. Now, those two fundamental motions I want to talk about today is the smooth downward acceleration of the tower's roofline. This is Tower 1 when it started to fall. And if we look at that and play it backwards, we can see it's falling down, but it's relatively smooth. Now, that motion has been studied by several people. One of them, of course, is David Chandler, and he actually tracked that downward motion. He plotted the velocity as it went down. And when he did that, he found that indeed it's a smooth downward acceleration. That is, there's no jolts, there's no impact, if you will. But that acceleration was not at free fall speed or free fall acceleration. I think there's a lot of misinformation out there. Some people, when they get into this, they're making the assumption that it was free fall for the towers. It was not. It was actually around, he measured it about 64% of free fall. But again, the key thing here is not the rate of acceleration, it's the fact that it continually accelerates smoothly, again, with no halting or no impacts or jolts on that motion. So that's the first key motion we want to study a little bit more in depth. There was also many horizontal motions, and that was from the debris blowing out laterally from the perimeter walls. There was multi-ton segments of perimeter walls blowing out, and those too have been measured anywhere from 40 to well over 70 miles an hour blowing horizontally outward. And there were some films taken of this, and we can actually see this, we can observe it today. Here is those outward motions blowing out. Notice that they're not even straight across, they're sort of on one half, and then the other half tends to catch up with it. But again, that's the outward motions that I want to talk about today also. So if we put these two motions together on Tower 1, we have that downward motion, but we also have that horizontal outward blowing out motion. And those are the two things that we want to look at a little closer. Now, behind any acceleration, regardless of its acceleration, there has to be a net force in accordance with Newton's second law. And I think it's important to understand that we're talking about a net force acting on an object, because there's forces all around us. Right now you have forces acting on you, but you're not accelerating. That's because there's no net force acting on you. So when we talk about Newton's second law, we're really talking about the net force acting on an object. And that force is proportional to the acceleration that we can observe. It's hard to see forces, but we certainly can observe objects that are accelerating. So that's sort of how we can tell when we have a force acting on an object, we have an acceleration. Now, the direction of any motion or acceleration is always in line with the direction of the applied net force. That's a pretty logical statement. If you have a computer mouse next to you, as you push that computer mouse horizontally, the direction that you push it will make that mouse accelerate. It's the same thing if you have a car. If you push on a car, you push on any object, the direction you push it in, the direction of the motion or the direction of the acceleration is always in line with the direction of the applied net force that's acting on that body. It's pretty logical. And so here's an old power hacksaw I happen to have in the barn, and here we have an acceleration back and forth, and the net force we can see is pushing on that link back and forth, again, just to kind of prove the obvious, if you will. Now, that direction of net force is also independent of scale. That is, if we see an object moving horizontally across your desk, whether it's, again, your computer mouse, or whether it's a pencil, or whether it's your telephone being pushed across the desk, we know that if the direction is the same, then the force behind that direction is also the same. And so the size or the shape of the object doesn't matter. It's totally independent. So that's one of the laws we can apply here as we start getting into this thing. And here we have a little model and a little parabolic trajectory. That parabolic trajectory, the force behind that was also a parabola. And whether it's a small little catapult or something large, if we want to throw a human being into a net, that trajectory and that force behind it, the directions are the same for both of them. So, and obviously neither one of those things scale. Not only that, the sequence of forces that causes a series of accelerations are also independent of scale. So if you're driving down the road and you're turning the steering wheel back and forth as you're weaving down the road, the sequence of forces that were applied to your car could be the same as a little small toy car if you also make that toy car weave back and forth. So the sequence of forces that made the accelerations are the same regardless of scale for any object. Another example is a howitzer, a large cannon. A howitzer and a handgun have similar sequences of force that causes all the motions that we observe, even though the handgun and the howitzer don't scale. Here we have a handgun going off with all kinds of motions going on, including the bullet accelerating and the slide coming back and the casing coming out of there. That sequence has to be just right to cause those motions observed. If the sequence is wrong, the motions won't match it. So By observing these motions, we may not be able to tell exactly what caused the force, but the motion of any smaller model object which matches a larger object's motion must have a similar direction and sequence of force. Again, even though the two objects don't scale. And the reason I'm sort of beating on this scaling issue is a lot of people will say, well, my models don't scale with the Twin Towers. Well, I'm not trying to scale the Twin Towers. I'm trying to scale fundamental laws of physics, whether it's heat or whether it's motion. We're talking about the fundamental laws of physics that are independent of scale. For example, students use all the time the motion of a ball on a string to demonstrate the motion of the moon orbiting the Earth. It may not be exact, it might be a little bit of an ellipse, but basically a ball on a string has the same force and the same direction as the moon going around the Earth, even though those two models don't scale and are obviously grossly different in orders of magnitude. But again, that's a model of orbital motion. Now, mathematical equations and computer animations were used by the officials and the mainstream media to explain how those towers fell. But any equations, no matter how complex, or any computer simulations must match experiment to be proved correct. And Richard Gage touches on the experimental method, and experiment is the core of the scientific method. The scientific method. Experiment is the core of the scientific method. When we have something we're not sure of, we ask a question, we gather all the information, we construct a hypothesis based upon all the information gathered. But then if you don't, you have to test your hypothesis by doing an actual experiment to see if it's true. And if it's not true, you have to go back and start all over until you can finally get the hypothesis to match real-world experiments. And that's, again, where I try to come in. I try to do real-world experiments, so no matter who does it, it can be replicated. Now, Richard Feynman was a theoretical physicist in the 20th century, one of the most famous ones if you research him. He was part of the Manhattan Project for the atomic bomb. He was also received a Nobel Prize. He was also on the what's called the Rogers Commission of the Challenger explosion back in 1986, and it was he that came up with the experiment of an O-ring dipped into some ice water with a C-clamp on it that explained the problem with the O-rings in the Challenger with the cold morning, the cold weather that was out there that morning. So he was very famous, and he was actually kind of a humorous theoretical physicist. And he understood how critical experiment is, because he's probably seen a lot of nonsense, if you will, out there in his life. And he knew that experiment is the key to weeding out the wheat from the chaff, if you will. And this is him teaching a class.
If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Now, for the Tower Demolition, the National Institute of Standards and Technology, they said that they were unable to provide a full explanation of the total collapse. They only went to what's called collapse initiation. They brought it up to the point of collapse, and then they basically waved their hands and just said, well, collapse was inevitable. So here we have one of the largest, if not the largest, mass murder of Americans on Earth, with the largest, in America, I'm sorry, and also some of the largest structural failures. And they were unable to provide an explanation of the total collapse, which right off the bat seemed kind of odd to me, because it's such an important issue for future structural design and for solving the mass murder. But two official theories came out that were promoted for the tower's destruction over the last 15 years. The first one was what's called the Pancake Theory, and the second latter one that was promoted was what's called the Piledriver Theory. Those are the two primary theories that are still used by many people to explain how those towers fell. There's also an unofficial theory that is not and was not promoted. but is being promoted by people who are doing research and studying those towers and how they came down. And that's the controlled demolition theory. And we're going to take a look today at all three of those theories. The pancake and the piledriver theory was never proved by experiment. So the question is, can we make a real model or a real experiment to determine which motion, the downward motion and the outward motion, and therefore which force must have come first? And which of those three theories best describes the motions we observe where those towers fall? Now, the pancake theory relies on the downward force from gravity alone to cause all those motions that we observed. That's the only force. Gravity, of course, is a force, and the only force we can rely on is the downward force from gravity. Yes, we acknowledge a plane's hit, and yes, there were fires that may have weakened it in the upper section, but once it started, after collapse initiation, the only thing involved was gravity. So we're assuming with the gravity that it must be down first, that downward motion first, and then an outward motion after that. So I call that a down and out theory. The FEMA and the American Society of Civil Engineers jointly put together a report that tried to explain how those towers came down. And their theory is what we call the pancake theory, where the floors broke away and they slammed down on the floors below it and continually accelerated down, destroying the entire tower.
Once the trusses failed, the floors they were holding cascade down with a force too great to be withstood. The result is what's called a progressive collapse, as each floor pancakes down onto the one below.
Now, that was the PBS scientific channel explaining to the public how those towers came down. And in the beginning of that clip, you'll notice that they didn't have any perimeter columns at all. They only had the floors. And at the end of this clip, you'll notice that there's still a lot of those core columns, all the core columns that are still standing. And the pancake theory really didn't explain how that core came down. And yet we know the core columns did come down. Also, this is a computer animation or a computer simulation that we were shown to explain what happened. And frankly, I believed it at the time. I mean, why would they say anything differently? It must be true. It's the PBS, it's the American Society of Civil Engineers telling us what happened. There's no reason to doubt it. But in hindsight, what we are really looking at is a computer animation of what happened, no real experiment. So if we're going to make a model, we should make that model so it's pretty close, if possible, to the actual thing that we're modeling. And for a building or a bridge, there's a couple of key structural design parameters when we design things. The first, of course, is strength. Obviously, the building or bridge has to be strong enough to carry its own weight, what we call the dead loads. For a building, it has to carry all the live loads, and the live loads are the people that occupy it, the furniture, the fixtures, and also things like hurricane winds and that type of thing, which are quite large on a tall tower. So all the columns and the beams have to carry the dead loads, the live load, and then on top of that, we also add or multiply by a factor of safety to make absolutely sure that that building is going to be strong enough to carry all those loads acting virtually simultaneously. The other thing we look at is what's called serviceability. Serviceability has several elements in it, but one of the key elements is called deflection. We want to make sure when we design a bridge or a building that the building doesn't move or the floors aren't too bouncy. Because if they are too bouncy, then it's uncomfortable. And like a tree blowing in the wind, a building can be perfectly strong, and yet it deflects so much that we're just not comfortable in there. And so that structure would not meet serviceability requirements. And so we have to strengthen the structure even more to make sure that we meet deflection. So any test model should at least be able to support itself with similar deflection limits for the applied load. And in other words, any model should be realistic and not just a house of cards that's all poised, ready to collapse. And so that's what I was trying to do here. So what I did is I grabbed, to test the pancake theory, I grabbed some pieces of cement board that I had stacked up. And I took a 20-pound steel block. It's a big chunk of steel, and I weighed that up. And then I put that steel block on the, I spanned the cement planks about 19 inches apart, and I started measuring with a straight edge what the deflection was for that steel block. And I did it for different numbers of planks for my model. I did it for 1, 2, 3, 4, and 5. And when I did that and measured it, I found that 4 planks would meet the deflection requirements for that particular 20-pound load. And anything less than that, 3, 2, or 1, would exceed deflection requirements. So any model made with a with less than 4 planks would not meet a deflection requirement. So it would not exactly match any kind of code. So I then made a wooden tower so I could place the planks in there, and I could either have 1, 2, 3, or 4 planks in there, and I could put any spacing I want. And then at the top, I suspended that 20-pound steel blocks with a fishing line, and I would get my camera set up, and I'd crawl up on top of the roof with a torch, and I would lean over, and when the cameras were rolling, I would just cut the torch with a fishing line so it would travel straight down and plumb. And let's see what happened when I did that. And what we're looking for is for a continual downward acceleration. So the weight of the steel block adds to all the weight of the floors and accelerates down to the ground. So here's my first try with 4 planks, which do meet deflection criteria. And as you can see, that block decelerated rapidly. It did not accelerate, even though the underlying planks below had the additional weight of the upper planks. Here it is in slow motion. Again, it's pretty obvious that it decelerates. I was going to track some of these things. That's why I had that target painted on the end of there. I was going to do like David Chandler does. Instead, I bought a slow motion camera so we can all see what really happens here. Then I decided to do an unrealistic experiment just for fun, and that was to drop it on only 2 planks, which way exceeded deflection. Again, to see if that steel block would continually accelerate down. By the way, the noise in the background is the torch that's burning to cut the line to let that thing drop. Here it is in slow motion. It obviously goes down further, but again, I think we can all see that the top decelerates. It doesn't accelerate. The Twin Towers accelerated. So this motion of the steel block does not in any way match the motion, the downward motion of the Twin Towers. In fact, it's just the opposite. Rather than accelerating, it's decelerating. So again, the motions observed by experiment using the Pancake Theory does not match the motion observed at the towers. And as Richard Feynman would say, well, we can discard that because it's wrong. And in fact, as a few more years went by, as NIST, the National Institute of Standards and Technology, did further research, they too claimed and made a statement that NIST findings do not support the Pancake Theory of collapse. So if you hear today about, oh, the towers just pancake down, you can let people know that, well, in fact, the government even says that they don't support the Pancake Theory. So in addition to it not matching experiment, the government and NIST does not even support the Pancake Theory of collapse. Well, the next theory that was promoted is called the Piledriver Theory, and that also relies on gravity alone to drive down the towers once the initiation started. In other words, picking up where NIST left off. That's another what I call a down and out theory. All the motions we saw were down and then out, but it was driven by gravity alone. And that was based upon a mathematical paper. That paper, with a lot of complex equations, were written primarily by a professor of Bazant, I believe at Northwestern University. And that paper came out, the first one came out 2 days after the event. So I think it came out on the 13th of September in 2001. So here he was, he already had the mathematics all figured out as to why those towers came down. And there were subsequent revisions, but fundamentally, the theory goes like this. The upper section was weakened by the plane impact and the fires over time. And the upper floors, representing somewhere between 12 and 15% of the upper floors, started moving down on the lower cold stronger section. Now the towers, like virtually all tall structures, were tapered. Visually they weren't tapered, but structurally they were tapered, in that the core columns and the perimeter columns were much, much thicker at the bottom and got thinner and thinner at the top. And again, just like a tree is thick at the bottom, but it gets thinner and thinner at the top, most trees anyhow. And so it makes sense, we're kind of following what nature does, because the bottom has to be stronger to carry all the additional weight from the top floors. So when the top block, we're going to call it a block, when the top block started moving down, he calls it the crush down phase. That top block, he is saying, mathematically crushed down the larger 85% of the stronger structure below, all the way down to the ground without crushing itself. And then when that top block got all the way down to the ground after the crush down phase, that top block then, once it hits the ground, crushed itself back up in the crush up phase. And so we just have a pile of rubble, and there are no floors. In fact, when you look at ground zero, there's not even the roof left. It's completely gone, even though there was no load on the roof. You'd think you'd see an acre of roof there at least, but no, that was gone too. And so this was called the crush down, crush up, or the Piledriver theory, that was promoted based, again, just on mathematical equations. But there's some questions with that. Newton's laws are independent of scale. In other words, when we use Newton's second law, and most of us have heard of that, F equals ma, that is independent of scale. It doesn't matter if it's the moon or that ball on a string. Newton's laws tend to work in Newtonian physics regardless of scale. So the forces that Professor Besant used in his paper, I guess the question that I have is, are those forces involved with this crush down, crush up analysis independent of scale, just like Newton's laws? And will those equations and result work on a larger structure or a smaller structure? And if so, how much larger and how much smaller? And will they work on any tall tapered structure? Would they work on a tree? If we cut a tree and dropped the top 15% on the bottom, would the tree below it turn into dust? Or are there limits to his equations and size as to when the crush up and crush down system applies? The paper, I don't think, clarifies when those equations will apply, but I'm going to make the assumption that it should be independent of scale like Newton's laws. So I decided to make a model and see if we could test this thing. Again, this was just based on mathematics. There was no real model to demonstrate this thing. So I took some of those cement planks and I cut them in half and I bored some holes in it. And I made some steel core columns, if you will, to guide those little floors so my model wouldn't tip over, because I was going to make this thing pretty tall. And what would happen, I made it so tall that it would want to tip over. So though my core columns, unlike the towers, were not there to hold or support the floors at all. Matter of fact, they were independent. My core columns were not connected to floors. They were only there to guide those floors so I could observe the motion of the floors. And so here's my core columns that I built. It's just basically some 3/4 inch pipe. They were about 10 feet long, set in some concrete. And I built that again to support my little model. Now, a good model really should be made out of similar material. And in the case of the towers, it's primarily steel columns and open web bar joists with a concrete floor on it. And I tried to use some steel walls, whether I wanted to use chicken wire or rabbit wire or needles or anything made out of steel and concrete, but I could not get those things to drive down by gravity alone. So in order to give the benefit of the doubt to the crush down, crush up theory, I decided to make some very flimsy walls in order to get those results predicted, again, by the crush down, crush up theory. And I decided to use, to start with, some pizza box supports. When we buy a large pizza, many times in the middle of that, there's a piece of plastic there to keep the cheese from sticking to the roof of the box. So I bought about 1,000 of those things so I could play with them. And I bought about the cheapest ones I could find because I wanted them to be weak, again, to give the benefit of the doubt to the theory. And so here I am. I took about the upper 15% of the floors, I suspended them up on top, and I dropped them down. And what did we observe? Well, we observed that the top stopped rather abruptly. It stopped very abruptly. It did not continually accelerate down, nor did the top portion drive down all the structure below. It just stopped. So I decided to take out the supports on the upper floors, thinking that, well, maybe that was absorbing too much energy, and I just stacked them all together and dropped it on there. And the same thing, I was able to break one of my little supports, but again, it abruptly stopped. That motion of that top upper block decelerated. It did not accelerate, and it certainly didn't drive itself all the way down to the ground and crush down and then crush itself back up. Here it is again in slow motion. We can see there's an abrupt deceleration, unlike Tower 1. So then I said, well, maybe I should build a house of cards. Maybe I should make an unrealistic model that does not meet deflection criteria. And I wanted to make a very, very weak system that was basically on a hair trigger and poised to collapse. And just like the 9/11 Commission, or like one of the commissioners said, I wanted to set them up to fail because I wanted to get those motions observed. And so I took those pizza supports and I turned them sideways, which is extremely weak and extremely high deflection. And I stacked them all up. And yes, I had more on the bottom than the top. I had to, otherwise the bottom would just crush itself. Then I put 15% of the floors on the top and dropped it down on the very weak supports that did not meet deflection on the system below. And here's what happened. And so there we have it. So there we had a top block of floors that drove itself all the way down, and we also got some horizontal motions out of that from the from gravity alone. So you'd think that, well, hey, maybe we're onto something. Now, the core columns are still there, and the floors are still there, but nevertheless, we did get some motions that were downward and outward. But the problem is, when we slow it down, when we look at our slow motion camera, what do we see there? We see that it slowed down. It did not accelerate continually down. It decelerated dramatically when it hit those floors. And that's not what happened at the Twin Towers. When those supposedly hit the floors, that top section accelerated. It did not decelerate. Well, then I decided to make even weaker walls, because again, I'm trying to get this to drive itself all the way down. So I made a bunch of paper walls for my Piledriver experiment. I took some ribbons of paper, and on the top sections I didn't have any supports, but as I went down I did have to add some matchsticks, again, because otherwise my model would just crush itself down during the process of building it, because those paper walls were very, very weak, especially when I had all the load above it. So I did use some matchsticks to help support the lower floors, just like the tower. So there was structurally tapered, a little bit stronger on the bottom than it is at the top. And I dropped again a 15% section down onto those paper walls. And if you look at those paper walls, they're all deformed, and the floor, my little floors, aren't parallel. They're all deformed, and they do not meet any kind of deflection criteria, unlike the towers. But even when I dropped that, it did not accelerate down. Once again, it decelerated. So then I thought, well, maybe if I just weaken my model with fire, will the top section accelerate down if I light my model on fire? Because that's really what happened at the towers. There wasn't a top section drop through the air that hit the bottom. It was actually weakened by fire, so goes the official story. And then once it was weakened, the top section just accelerated all the way down to the bottom. So I lit my little model on fire. And once the fire burned the walls, the paper walls, of course, it did weaken enough, and it started to accelerate down. But you'll notice that it starts, and once again, even with very weak paper walls, it does not continue to accelerate down. So the motions observed by experiment using the Piledriver theory does not match the tower's motions. And as Richard Feynman would say, well, then that hypothesis has got to be wrong. But what if the sequence of force that I assumed was all wrong? What if the force was not down first with gravity and then out, like the Pancake and Piledriver theories assume? What if instead that force was out and then down? Well, we would need to apply some internal force first, and so I needed some explosives. So I took that paper wall and I put a firecracker inside it, and I stacked half the floors above it. Again, it deflected quite a bit, and I lit the firecracker. And for my little test, this is what we got. It was out, and then the top accelerated down, and it bounces a little bit there. It was on a 55-gallon drum. And I did it again. I put all the floors on top of it and lit it, and it goes out, and then the top uniformly accelerates down, even though they're not tied together. So there's an outward force first, followed by the gravitational force pulling it down uniformly. But I needed more explosives in order to test this theory in a taller, much taller structure. So what I did is I started stacking up my little floors and my little paper walls, and I ran a continuous fuse on the inside. And then I bought some perfectly legal firecrackers, and I set them in those floors, and I started building this thing up slowly, being careful. You can see this one here has got 3 matchsticks in it as I'm getting halfway up, and eventually I'll go up to no matchsticks, because if I didn't do that, again, those walls would just crush itself. As a matter of fact, it did several times when I was trying to build this thing. It's kind of tedious, and I have to take it all apart and start all over again, because my little paper walls couldn't hold this whole thing up. But I kept going, and I kept stacking up my firecracker as I built this thing. I'd slide down each floor, if you will, from the top all the way up, slowly building this thing until I got a tall structure. Now, if you look at this structure, you'll notice my paper walls are deflected. The real structures was not deflected. And I, quote, wired this thing, if you will. I put my fuses out at about the same place where the airplanes hit on the real towers and left them hanging out, and simply ran up to the thing and lit it with my Burns-O-Matic torch, and then ran like crazy and watched what happened when all these go off. And this is what happened. Now, it wasn't perfect, but you'll notice that the motions were out first, and then, of course, it was down. It was out and down. Let's take a look at this thing using my slow motion camera. And let's also look at a second one I did. I actually did many of these, but I think I posted on YouTube 3 or 4 of them. Let's look at this first one in slow motion and observe and think about what we're observing here with the motions that we're seeing. And again, I'll show a second one and also play that one in slow motion. I put this thing to a little music by Beethoven. I want you to think about and observe what happened there. Now, again, those motions certainly weren't perfect by any means. They were sort of halting, but we did have some horizontal motions and some downward acceleration of the top. So it appears that if we apply a horizontal force first, the top will continue to accelerate down by gravity. In other words, it's out first and then down. But if the horizontal force stops, the downward motion always stops. And you can see this on some of my failed experiments where I couldn't get them all to go timed perfectly. In fact, it's very hard to time mechanical fuse, just doesn't want to cooperate. But the one thing we can learn is that the top will only accelerate down if there's a horizontal force applied to the walls first. It's out first and then down. It's out and down. It's not down and out. And so the direction of the force behind the horizontal motions blowing out those walls was from the inside. It had to be because the material blew outside. It wasn't from some space lasers or some external force. It had to be from the inside because we know the direction of the force is always in line with the motion we observe. And the sequence of the forces in those towers had to be first be out and then down. But both the pancake and the piledriver theories disagrees with experiment. So they're wrong. Here's a side by side. If we see the pancake, the piledriver, both of them stop. It's only the controlled demolition where we have similar motions between the tower's roofline and my little demolition. Now, of course, I might be wrong, and I'm not the best model maker in the world. But if I'm wrong, you can say what you want about me, but you need to prove me wrong by experiment. And anyone that believes the official story can make their own experiment with a tall, tapered, self-supporting structure that doesn't have any deflection, made of steel and concrete, and then weakened by igniting a fire in the upper floors, and then see if that structure will completely destroy itself, just like we saw the towers destroy themselves. It's got to look like this. That tower isn't collapsing. That tower is being blown outward. It's being blown up. That is not a natural thing. But again, if you think I'm wrong, then all you need to do is make an experiment to mimic the motions we observed that day. And of course, the average person may not understand this or really care. Well, let's face it, we're all leading our own lives, and we have things to do, and sometimes we just can't be bothered with things like this. But one would think that with all our technology in America and all our experts, somebody could make a model to demonstrate what we saw that day. But so far, none of them can, or none of them have. FEMA, the American Society of Civil Engineers, the National Institute of Standards and Technology, the AIA, some of the best model makers, universities, engineering, physics classes, nobody can make a simple experiment that demonstrates the force behind the motion. And with that, Andy, I'll open it up to questions.
Well, I want to thank you for putting that presentation on. We certainly do have a lot of questions coming in. The first one sort of challenges what you were talking about scale, and maybe you can give a statement in answer to this. It says, many supporters of the official 9/11 story dismiss your experiments because you don't take scale into consideration. Is there anything you can do once and for all to prove that scale is not relevant when performing experiments involving directions of net force?
Well, again, I think scale is important when we're talking about some energy issues, but it is not. It is independent. Newton's laws are independent of scale. F equals ma. Force and accelerations are independent. I would love it if somebody could build a real scale model. And like I say, you'd think with all the technology we have, if they wanted to prove the official story, we scale models all the time. I don't, but model makers do all the time. They are built to scale. So that's why I tried to, again, use only fundamental principles that are independent of scales. The melting point of steel is independent of scale. Eutectic formations is independent of scale. And so that's why I want to focus on force. Force is independent of scale. And again, I guess the only thing I can say is forces and direction of force, as far as I know, have always been independent of scale. And that's, again, why we can use a little ball and string to discuss the forces involved in orbital motion. So maybe somebody else can make a scale model. I'd love to see it, and I'd like to see an experiment on that.
Great. Our next question rather is says, using Jonathan Cole's support structure with the horizontal cement planks showing how the cement planks eventually decelerate a falling weight that breaks through several planks. If you gradually increase the distance between those planks, will you eventually reach a point where the planks no longer stop the falling weight? Thank you.
Yes, yes, you certainly will. If you make those planks weak enough, if you just put one plank in there and you space those quite a ways apart, yes, that upper steel will drop and go all the way through them. But as it impacts, there has to be an impact at each floor. And if we measure that very closely, there will be an impact and there will be a momentary jolt or deceleration. But certainly, if you have a large enough weight to drive through a weak enough support, of course it will go all the way through it. But again, we really should have whatever that weight was supported above, it ought to be able to support it with minimal deflection, just like a building. Those towers didn't deflect when they were standing there. So that's why I brought in the whole issue about deflection. Yes, we can make a house of cards. Yes, we can drop I could drop that 20-pound weight on my paper walls, and certainly it would drive it all the way down. But those paper walls would hardly even hold the weight, let alone not deflect. But the answer to the question is yes, you can get something to drive all the way down.
Okay, our next question asks, besides computer models, what experiments, if any, did NIST conduct to make its point?
Well, you know, as Richard Gage points out, and many know, there was actually 3 large collapses on 9/11. The Twin Towers went down in the morning, and then later in the day, Building 7 went down. And unlike the towers, Building 7, in fact, did come down at free fall. And NIST used a computer model for to demonstrate what happened there. But they did, for Building 7, I don't believe they did any experiments whatsoever. For the Twin Towers, I don't believe they did any experiments on the motion, but they did do some heating experiments with the open web bar joists and some of the floor systems. On my understanding, Kevin Ryan's done quite a bit of work on this, but I believe they did some experiments, but unfortunately, most of their experiments didn't support their theories. The other thing they did, I think they did a shotgun blast experiment where they actually took a 12-gauge shotgun, they blasted away at a steel plate with some foam on it. And they said that that was equivalent to an airplane stripping all the asbestos insulation inside or foam insulation inside those towers. So they did some, the bottom line is, yes, they did some experiments on certain elements for the towers, but they didn't do any experiments on the actual destruction itself.
Okay, our next question says, the weight in your first experiment tips to the side as it hits the planks. Is this what the top of the Twin Towers should have done?
It's my opinion that the Twin Towers should have done that. If all those core columns were severed, or if they were all heated very hot and weakened, it's my opinion, being so tall, that when the top came down, and if it had actually impacted, if there was an actual jolt and it impacted, I would think that, yes, they would bounce off to the side. Again, I go back to nature. To take a chainsaw and cut a tree at the top 20 feet of a 100-foot tree and drop it on the 85% below, don't you think that that top is going to hit that and then bounce off and go to the side? I would think it would. I don't think it would drive all the way down and turn the lower section into powder or dust.
Okay, our next question has several questions included in a long paragraph, so we'll hit this one, but we want to make sure we hit everyone else's too. So we'll do the first question. Just to clarify, when you talk about acceleration, that tells me the velocity is increasing. Once the failure started, was the velocity of the fall constant or accelerating?
Okay, yes, acceleration means a change in velocity. And yes, it does mean that the velocity wasn't increasing. I think if you go to David Chandler's graph in his videos, I think what he's doing, he's plotting velocity. I believe he's plotting velocity versus time. So yes, the velocity is continually increasing, and that's what acceleration means. Again, it's not a free fall, but it is increasing.
Okay, and then it goes on to ask, might the performance of the pile driving model behave differently if the structural strength of the wall was different, such as might have been the case with the towers?
I'm not sure I understand the question. I know a little bit about the perimeter walls. They were basically box columns that were thick at the bottom, several inches thick at the bottom, tapering all the way up to, I think, about 1/4 of an inch near the top. So they were tapered wall panels that were bolted and welded together, certainly bolted together all the way up. And then the core columns, and I might be digressing from the question, the core columns were also extremely thick at the bottom, 6 inches or so or more, and those also tapered all the way to the top. So that was the main beef of the structure, if you will, the core columns. But the perimeter columns took all the compression loads and tension loads from hurricane, from wind forces. So, Andy, I'm going to have to ask you to repeat that question. I don't know if I fully understand the question.
Sure, and actually, it's going to sort of combine this question and the next one from this person. Essentially, if you had exhaustively built the model basically just like the Twin Towers, you know, with the same kind of structure and potentially the structural strength of the walls if they were different, if it was more like the Twin Towers and you had taken years to do this, let's say, do you think it might have made any difference in the end result of the experiment? Do you think that there could have been a different result?
Fundamentally, no, but yes, there would have been a difference. And I kind of touched on that when I attempted to make the towers, my little model, out of steel. I think if I really made small box columns for the perimeter and the core columns and had little open web bar joists inside and little concrete floors on them at the same geometric size as the towers, I think you would see a difference. I think you would see almost no deflection at all. You wouldn't see anything breaking down at all. I think you'd see an immediate arrest of the downward motion. But again, fundamentally, I'm quite sure you would still see a deceleration because, again, I tried to make it out of steel, and I couldn't get anything to work with steel at all. Again, I tried some rabbit wire and some other things, and I mean, other people can try it. Maybe they can get it done, but I just couldn't make it happen.
Okay, our next question asks, if a tower collapse always involves deceleration as the top meets the successive floors, does it not logically follow that all similar tower collapses will self-terminate, stop? If true, then is it even possible for a total floor-by-floor building collapse to occur?
Yeah, I think a tall tower, if it catches fire, matter of fact, we have real life experiments on this, real life fires that happen. First of all, I don't think they will collapse. I think they all will decelerate if they're a tapered tall structure that we're talking about here. I think that actually will happen. It'll rapidly decelerate. And I think pancake collapses are extremely rare, especially in American modern steel construction. They do happen. Normally you'll see them happen with an earthquake. You will see, especially with concrete floors, concrete structures, you will see a stack of floors with a real pancake type failure. And normally it's with an earthquake. I haven't seen it really with a fire on a full structure. So, and a lot of times we'll go in there and we'll rescue people that are caught between the floors. But the one thing we see with pancake collapses is we actually see the floors are all stacked up there and the people are trapped inside. We didn't see that at ground zero. We didn't see any floors. Like I say, we didn't even see the roof. It was completely turned to powder. It was completely blown up, except for the steel, but the concrete was totally blown up and turned into big billowing clouds of pyroclastic flow, if you will. So the answer to your question is yes, pancake collapses can happen, but they're pretty rare with a steel structure. And I don't think there's been one in America for decades, to be honest with you.
Okay, our next question asks, is selecting the floor's characteristics based on deflection of the floors relevant for the models with circular walls?
Well, I think it is. I think any model should be able to support itself. And let me tell you, one of the reasons I use circular walls, I mean, you could use square walls, but I could only legally buy certain size firecrackers. So I had only a certain amount of energy to blow this thing apart. And so admittedly, the walls are pretty weak. And again, if I had used steel, unless I bought dynamite, which I can't get because it's illegal for me, I couldn't blow steel up. So again, I had to go with some weaker walls in order to get the motions I was looking for, or the motions we observed. So the little cement plank floors I used, and that's because that's what I had. And it seemed to work pretty good. At least it was some sort of cementitious material. And the round paper walls, I guess you could also do it with square paper walls. But again, I'm focusing on the motion and not so much trying to make an exact model of the towers.
Okay, next question is asking for a comment from you on this statement. It says, the pancake theory appears to be inconsistent with the tipping of the top of the towers. Do you have a comment on that?
Yeah, I think, what was it, Tower 2? I think if you look at the beginning of the destruction of Tower 2, it actually does tip over quite a bit. And then all of a sudden it just starts destroying itself, both the top and the bottom. So yeah, I think the pancake theory is inconsistent with the tipping of the towers, and it's also inconsistent with a whole bunch of things, which may be why the NIST never supported the pancake theory.
Okay, our next question just came in, and it asks, what was the strength of the strongest connections in the towers per PSI? Why did you neglect trying to create accurate energy values in your experiments?
Right. In the towers, the open web bar joists were actually connected to the perimeter columns with some bolts, and they were also connected to the core columns. And they were bolted and welded to that. And then on top of the concrete, on top of the open web bar joist was a corrugated pan decking with lightweight concrete poured in that. I don't know what the PSI was on that concrete. But the reason, again, the reason I was not focusing on energy issues here, I was focusing on force issues, again, because force ties to Newton's laws. We can understand direction of force, we can understand sequences of force, rather than getting into complex energy equations here. I wanted to stick with just a simple force issue here, force and direction. And so I think had I made it, again, out of steel, and had I actually connected my core columns to my little individual singular floors, again, they just floated on it. They were guideposts only. I think if I actually connected them to that and actually built some perimeter walls rather than just those paper walls, well, I don't think you would have got anywhere near what we saw with either the Piledriver or the floor by floor collapse on that. I was actually trying to favor it in favor of the crush down, crush up theory. That was my goal because I couldn't get anything to work had I not done that.
Okay, our last question is going to be a combined one that doesn't focus on the science so much as getting this information to others. One asks if we've tried to reach any presidential candidates with the scientific information. The other one says that this should be on PBS, and how do they get it on PBS? So I'm going to comment on that myself. And John, you're certainly invited to comment too. There have been outreach done to presidential candidates regarding the science of the information being presented today by Jonathan Cole, the information that's presented by Richard Gage. We constantly have outreach to political candidates. In fact, if you go to the top of AE911Truth.org right now and click the What You Can Do tab, there is a letter that you can send to your senators asking them to expand a certain piece of legislation to include points about Building 7, which is not being talked about today, but has been talked about in other webinars. If you want to help us out, you can certainly volunteer, and we encourage you to do that right on the same webpage. Fill out the form, and we will get in touch with you, and you can be a part of getting that information to others. John, do you have any comment on that?
No, and I think just to mimic what you said, I think we've been trying for many, many years to get this on mainstream, but I think the fact that it's not on mainstream kind of tells us something about the information that the average American public is receiving, that it's controlled. They only want to let out what they want to let out. And if anything, they try to demonize anybody who wants to think independently or try to do things independently. They'll try to demonize those people. They'll call them names. They'll do anything they can. But of course, they'll never show us. They'll never really fight the facts. So yes, that outreach has been made. That's what Richard Gage does all the time. And many others do also. But Richard Gage with the whole AE911Truth organization, it's exactly what he's trying to do by going out and trying to share this information, because it was a crime. It was a horrible crime, and there's been no justice on this.
Okay, well, that is going to wrap it up for today. I want to thank Jonathan Cole for coming on and making this very important and very good presentation and these experiments. We are going to be back next Sunday with this webinar series. So again, if you're moved by this evidence, please share it with others. Let other people, particularly if they have a professional background, like in building trades industry, let them know about these webinars and come to submit their questions. But we will be back again on Sunday. So thank you very much. And again, thanks to Jonathan Cole. Goodbye.